In 1964, a 26-year-old physicist wrote down correctly what every solid thing you have ever touched is actually made of. It was verified. It is now taught to every physics student on Earth, and his reward was to be called a charlatan to his face in a faculty meeting by one of the most respected theorists alive. His paper was forbidden and his seminar was cancelled. The man who erased him is in your textbook, and his name almost certainly is not. His name is George Zweig. He co-discovered the quark, and he insisted these particles were physically real when the safe move was to call them mathematics, and reality proved him right down to the last detail. Tonight you follow the whole buried trail, from the 80-page document a CERN director locked in a drawer, to the 2-mile machine in California that felt the particles he swore were there, to the Nobel that went to the other man, and finally to the reason you are made, almost entirely, of a prison holding things no one will ever be allowed to see. So get comfortable, and if you're new here, subscribe or join, because the part that should really unsettle you, the reason you are mostly made of something no one can ever see, does not arrive until the very end. If you want more of these buried science stories, the wider explorations across physics and history live on the Patreon. Let's go back to where this began. Somewhere in the archives at CERN there is a document 80 pages long, written in the winter of 1964, that correctly describes what every solid object you have ever touched is actually made of. Your hands. This screen. The chair underneath you. The water in the glass next to you and the bones holding you upright. All of it, down to the last structural detail, is built the exact way that document said it would be. And that document was never published. The head of the theory division at CERN forbade it. He told the department secretary not to type it, and when the man who wrote it had scheduled a seminar to explain it to his colleagues, a seminar he had titled, with the private gallows humour of someone who already sensed how this was going to go, Dealer's Choice, Aces Are Wild, the seminar was quietly cancelled and never rescheduled. The man who wrote it was 26 years old. He had just finished his doctorate under Richard Feynman, and a few years later, at a faculty meeting inside a university whose name has never once been made public, one of the most respected theoretical physicists alive would stand up and destroy this man's job offer by calling him, in front of the room, a charlatan. Here is the part that should stop you. He was right. Not partly right. Not right in spirit. He had written down, correctly, before almost anyone else on Earth, the architecture of matter itself. The thing he was proposing is now taught to every physics undergraduate on the planet as settled fact. It is inside every proton in your body right now, roughly 7 billion of them, each one assembled precisely the way he said. And you have almost certainly never heard his name. His name is George Zweig, and the reason you were never told about him is not that he was wrong, and it is not that his work was lost, and it is not some innocent accident of history. The reason is more disturbing than any of those, because the reason is that the version of this story where he does not exist was simply more convenient for everyone who came after him. It was cleaner. It had one hero instead of two. It had a good name lifted from a novel by James Joyce instead of a deck of playing cards. And so the physics establishment, without anyone needing to hold a meeting or sign a document or agree on anything at all, quietly settled on the tidy version and let the other one sink. I have spent an unreasonable number of hours inside this story, and I want to be careful with you, because there is a lazy way to tell it, and it is wrong. The lazy way is that Murray Gell-Mann stole the quark from George Zweig. He did not. The two of them arrived at the same buried truth independently, at almost the same moment, from opposite ends of the earth, and never compared notes until it was over. That is not the scandal. The scandal is what happened after. The scandal is that of the two men who found the same thing, one got a Nobel Prize and a word that entered the English language, and the other got called a charlatan, got blocked from a job, got his paper strangled in a filing cabinet, and eventually walked out of physics entirely to go study the inside of the human ear. And the field let it happen. And then the field forgot it had happened. And then the field started teaching your version of events, the one with the missing man. So the question I want to hold in front of you for the next couple of hours is not really who invented quarks. That question has an answer, and the answer is two people. The question is why the one who was arguably more right, the one who insisted these things were physically real when the other man hedged, is the one history erased. Because once you understand why he was erased, you understand something about how physics actually decides what is true, and it is nothing like the meritocracy you were sold. And there is one more thread, and I am going to plant it now and leave it, because it is where all of this is going to end up. The thing Zweig was right about, the thing that got him called a fraud and cost him his place in the story, is also the single strangest object in all of physics. It is real. It is inside you. And it is the one thing in the entire universe that you are structurally forbidden, by the laws of nature themselves, from ever seeing on its own. Not because we lack the technology, because reality will not allow it. Hold on to that. We are going to come back to it. And when we do, it is going to be worse than it sounds right now. To understand why any of this mattered, you have to understand what physics looked like in the early 1960s, because it was a mess. A genuine, humiliating, career-threatening mess. For 30 years the picture had been simple and beautiful. Everything was made of protons, neutrons and electrons. 3 particles. You could put them on an index card. A child could understand it. And then the particle accelerators came online, the big ones, the ones that could smash things together at energies nobody had ever reached before, and out of those collisions poured a flood of new particles that nobody had asked for and nobody could explain. Not a handful, dozens of them, then more than 100. Particles with strange properties and stranger names, pions and kaons and lambdas and sigmas and cis. Particles that lived for less than a billionth of a second and then fell apart into other particles. Every time physicists built a bigger machine, the machine coughed up more of them. They called it the particle zoo, and the name was not affectionate. It was an admission of defeat. A zoo is what you call a collection of things when you have no theory that explains why those things and not others. Enrico Fermi, one of the towering physicists of the century, reportedly said that if he had known there would be this many particles, he would have gone into botany. That was the mood. The most fundamental science there is, the science that is supposed to explain what everything is made of, had lost the plot so completely that its practitioners were joking about switching to the study of plants. And under the jokes was real fear. Because a science that cannot organize its own subject matter is a science in crisis, and everybody knew it. 2 men found the first way out, and one of them is the man this story is supposedly about, so pay attention to how he enters it, because it matters later. In 1961, Murray Gell-Mann at Caltech, and separately an Israeli physicist named Yuval Ne'eman, noticed that if you sorted the chaos of the particle zoo by certain properties, the particles fell into neat geometric patterns. Groups of 8, groups of 10. Gell-Mann, who had a lifelong habit of reaching for exotic names, called this the Eightfold Way, borrowing a phrase from Buddhism, half as a joke. And it worked. It was the periodic table moment for particle physics. The particles were not random after all. They arranged themselves according to a deep mathematical symmetry, a structure that mathematicians call SU3, and once you saw the pattern, you could do the thing that separates real science from storytelling. You could predict. The pattern had a hole in it. One of the geometric arrangements, a triangle of 10 particles, was missing its bottom corner. 9 of the 10 had been found in accelerators. The 10th had never been seen by anyone. And Gell-Mann, staring at the gap in 1962, did something audacious. He said the 10th particle must exist, and he said exactly what its properties had to be: its charge, its strangeness, and roughly its mass, because the symmetry demanded it. He was betting his reputation on a particle nobody had ever observed, predicted purely from the shape of an equation. In 1964, at Brookhaven National Laboratory on Long Island, in a bubble chamber the size of a small room, a team led by Nicholas Samios found it. The Omega Minus. Exactly where the pattern said it would be, with exactly the properties the pattern demanded, weighing in at roughly 1,672 million electron volts, almost precisely the predicted value. It was one of the great triumphs of theoretical physics. It should have settled everything, but it did not settle anything, and this is the crack that the whole story pours through. The Eightfold Way told you that the particles fell into patterns. It did not tell you why. A periodic table is a wonderful thing, but the periodic table of chemistry is only the beginning of the story, because underneath the patterns of the elements there turned out to be a reason, and the reason was that atoms are made of smaller things, protons and neutrons and electrons, arranged in ways that produce exactly those patterns. So the obvious, nagging, impossible to ignore question hanging over particle physics in 1964 was this: if the particles fall into these beautiful symmetric groups, what are they made of that makes them do that? What are the smaller things underneath? And that is the question two men answered at the same time without knowing about each other. One of them answered it in a 2-page paper that sailed into print. The other answered it in an 80-page document that a senior man locked in a drawer. Both answers were correct. Only one of them survived. Therefore, to understand how the wrong man got erased, you have to look closely at what he actually said, and in particular at the one thing he said that the other man refused to say, because that one difference is the seed of everything that happened to him. George Zweig was not supposed to be in Geneva. He was supposed to be at Caltech, where he had done his doctorate, but he had won a fellowship that sent him to CERN, the European laboratory outside Geneva, for the better part of a year, and it was there, working mostly alone, that he found the thing that would define and then derail his life. He was chasing a much smaller puzzle when he found it, which is how these things usually go. He was not trying to rewrite the foundations of matter. He was trying to understand why one particular particle decayed the way it did. The particle was called the phi meson, and its behavior made no sense. When a heavy, unstable particle falls apart, it tends to do so in whatever way is easiest, the way that requires the least energy, the way water finds the lowest path down a hill. The phi meson had an easy path available. It could have fallen apart into a particle called a rho and a particle called a pi, and by every rule anyone understood, that is what it should have overwhelmingly preferred to do. Instead, the phi meson stubbornly, overwhelmingly, decayed a different way, into 2 heavier particles called kaons, which was a harder path, an uphill path, a decay that should have been suppressed and instead dominated. It was as if you dropped a ball at the top of a hill and it rolled up the steeper slope on purpose. Nobody could explain it. Zweig explained it, and the way he explained it forced him to invent the thing that would get him called a fraud. He worked out that the phi meson's strange behavior made perfect sense if the particle was not a fundamental object at all, but was instead built out of smaller constituents. And if those constituents obeyed a simple rule about which decays were allowed, and which were forbidden depending on whether the smaller pieces could survive the transition or had to be created and destroyed. The rule works. It is real. Physicists still use it today, more than 60 years later, and they call it the Ozzy rule, and the Z in Ozzy stands for Zweig. His name is literally embedded in the physics, initialized and abbreviated, sitting inside a rule that thousands of people invoke without ever thinking about the man it is named after. That is a small preview of how this whole story goes. His fingerprints are everywhere. His name is nowhere. To make the Feynman behave, Zweig needed those smaller constituents, and once he had them, he realized they could not just explain one strange decay. They could explain everything. Every particle in the entire zoo. So he built the whole scheme out, and because he had a sense of humour, and because there turned out to be a natural way to think about them in fours, he called the fundamental constituents aces, after the 4 aces in a deck of cards. In his scheme, the ordinary particles were hands dealt from those aces. A meson, a particle like the phi or the pi, was made of 2 aces, an ace and an anti-ace, and he called those deuces. A baryon, a heavier particle like the proton or the neutron, was made of 3 aces, and he called those treys, deuces and treys built from aces. The entire particle zoo, every last exotic creature in it, reduced to different combinations of a tiny number of fundamental cards. And here is the property that made everyone recoil. The one that mattered more than any other, the one you need to hold on to. For the arithmetic to work, for the aces to combine into the particles we actually see with the charges those particles actually have, the aces themselves had to carry fractional electric charge. Not 1 unit of charge, not 2 units. Fractions. 1 ace carried 2/3 of the charge of a proton. Another carried negative 1/3. And to a physicist in 1964, this was not a bold idea. It was close to heresy. You have to understand why, because the strength of the taboo is the whole point. Electric charge was one of the most sacred quantities in all of physics, and it was sacred specifically because it came in whole units. Every electron in the universe carries exactly the same charge. Every proton carries exactly the opposite. You never saw half a charge or 1/3 of a charge ever, anywhere, in any experiment ever performed. This was not a vague assumption. It had been nailed down decades earlier, at Caltech of all places, by Robert Millikan, in one of the most famous experiments in the history of science, the oil drop experiment, for which Millikan won a Nobel Prize. Millikan had shown that electric charge is quantized, that it comes in indivisible lumps, that there is a smallest possible unit and everything is a whole number multiple of it. That was bedrock. That was the kind of thing you built the rest of physics on top of. And here was a 26-year-old proposing particles that carried 1/3 of the sacred indivisible unit, as if the unit were not indivisible at all, as if you could cut the uncuttable. Even Gell-Mann, who arrived at the same idea from his own direction, found the fractional charges hard to stomach at first. The story goes that when a colleague named Robert Serber floated the idea of a fundamental triplet to Gell-Mann over lunch at Columbia in early 1963, Gell-Mann initially waved it off. Fractional charges seemed absurd, and that reaction from Gell-Mann of all people tells you exactly how far outside the acceptable this idea sat. It was not a small step past the frontier. It was a leap over a wall that everyone had been told never to climb. Now I need to slow down, because we have reached the single most important distinction in this entire story, the fork in the road that sent these 2 men to such radically different fates, and it is subtle, and if you miss it, you will miss why one of them was punished. Gell-Mann and Zweig proposed the same particles, same number, same fractional charges, same combinations. But they did not believe the same thing about them. and what you believe about a thing turns out to matter enormously when the thing is this dangerous. Gell-Mann hedged. He was brilliant, and he was careful, and he had a reputation to protect, and he could see the fractional charges were a liability. So in his 2-page paper, he left himself an escape route. He suggested that the quarks might not be real physical particles at all. They might be, in his words, purely mathematical entities, a useful bookkeeping device, a way of organizing the symmetry without any commitment to actual objects you could in principle find. He even wrote that a search for real quarks with fractional charge that came up empty would help reassure us of the non-existence of real quarks. Read that again slowly. He was saying that the best outcome, the reassuring outcome, might be to find nothing, because finding nothing would mean these embarrassing fractional charge objects were just math after all, and physics would not have to face the possibility that the bedrock had cracked. It was a hedge, a brilliant, defensible, career-preserving hedge. Zweig did not hedge. Zweig thought the aces were real, physically actually, mass-carrying, spinning, dynamically interacting real. Years later, asked directly whether he had believed the aces were real particles, Zweig said something that cuts right to the center of him. He said the aces had dynamics, so it was hard to believe they were not real. They had mass. They had binding energy. They had spin. They had angular momentum. They had the intricate interactions that real objects have with each other. To Zweig, an object with that much physical structure, that much machinery, could not possibly be a mere accounting trick. It had to be a thing. And so where Gell-Mann built himself a door marked maybe it is only mathematics, Zweig walked out into the open and said, no, these are real, they are inside the proton, and one day we will understand how. That is the difference, and that difference is why the establishment could tolerate Gell-Mann and could not tolerate Zweig, because Gell-Mann had given them permission to not take the idea too seriously. He had built the abstraction with a shrug attached. But Zweig had made a claim. A physical, testable, falsifiable, reputation-staking claim about the actual constituents of actual matter. And a claim like that, if it turned out to be wrong, would make you look like a fool. Which meant that a claim like that, before it was proven, made you look like something worse than a fool to the people guarding the gates. It made you look like a charlatan, a man selling fractional charges that could not exist, insisting they were real, when the sober thing to do was to call them mathematics and keep your hands clean. I want you to sit with the cruelty of that for a second, because we are going to watch it play out in forensic detail, and it will be easier to bear if you already see the shape of it. Zweig was punished not for being wrong, but for being brave. He was punished for the precise thing that later turned out to be his greatest correctness. He said they were real. Everyone else said, carefully, maybe they are only a convenient fiction. And reality, when it finally answered, sided completely with Zweig. The aces are real. They are in you. But by the time reality got around to answering, the answer no longer mattered for George Zweig, because the machinery of the field had already closed over him and moved on. But before we get to how reality answered, we have to look at how the field closed over him. Because the mechanism matters. It always matters. When people tell you an idea was suppressed, they usually mean it vaguely, as a kind of atmosphere, a general climate of resistance. That is not what happened to Zweig. What happened to Zweig was specific. It had a location, a chain of command, an instrument, and a name. And once you see the specific mechanism, the vague word suppression turns into something much harder to look away from. To understand the mechanism, though, you have to know who George Zweig was before he walked into that building in Geneva, because the man the establishment tried to erase was not some rootless outsider who had wandered in from nowhere. He was a person, with a history, and the history is one of the most brutally ironic things I have ever come across, and it connects to what was done to him in a way that I still find difficult to talk about calmly. George Zweig was born in Moscow on the 30th of May, 1937. That year and that place should already be making the hair on your neck stand up, because 1937 in the Soviet Union was the height of Stalin's Great Terror and the years that followed. Across the whole of Europe were about to become the worst years in human history to be a Jewish family, which the Zweigs were. His father was a structural engineer, a man whose entire profession was the study of how to build things that do not collapse, how to distribute load, how to keep a structure standing under stress. Remember that. A man who spent his life on the physics of not falling down, raising a son who would spend his life on the physics of what holds matter together. The family got out of Europe, but only barely, and only because of a piece of luck so thin it is almost unbearable to describe. As the Nazi machine closed in, after the Anschluss in 1938, when Germany absorbed Austria, and the trap began to shut on Europe's Jews, the Zweigs made it to the United States, and eventually to Detroit. They were admitted, according to the account that survives, only after 2 United States senators from Michigan personally intervened on their behalf. 2 men in Washington had to reach down and pull this specific family through a door that was closing on millions of others. And here is the part that I cannot make gentle, so I am not going to try. George Zweig's paternal grandparents did not make it. They were denied entry to the United States. They were deported. And in January of 1942 they were sent to Riga, in Latvia. And they were murdered there, among the tens of thousands of Jews killed in that place. So the boy who would grow up to discover the building blocks of matter was, from birth, a person who existed only because a bureaucratic gate happened to open for him and closed on his own grandparents. His whole life was, in a sense, the product of an institution deciding, arbitrarily, capriciously, who was allowed through and who was not. He was made by an act of gatekeeping, and he would be unmade decades later by another one. I told you this connects to what was done to him, and I am telling you now, plainly, so you carry it the rest of the way. The man whose family was destroyed by gates deciding who counts spent his professional life on the wrong side of a gate deciding whose ideas count. The physics establishment did not murder anyone. I am not saying that. But the shape of the thing, the shape of an institution, quietly deciding that this person's contribution will pass and that person's will not. That shape was in George Zweig's blood before he ever wrote down an ace. He grew up in Detroit, took a degree in mathematics at the University of Michigan in 1959, and went to Caltech for his doctorate, which is where the story braids into the other man, because Caltech is where Murray Gell-Mann was. Zweig wanted to do theoretical physics. When it came time to find an advisor, he approached Gell-Mann, and Gell-Mann declined to take him on. So Zweig ended up working under Richard Feynman instead, which is one of those accidents of history that reads like a novelist trying too hard. The 2 men who would independently invent the quark, Gell-Mann and Zweig, were at the same institution, and one of them turned the other down as a student, and the student went to the office next door and studied under the one physicist on Earth whose intuition was arguably even more feared than Gell-Mann's. Feynman and Gell-Mann shared a flaw, shared a rivalry, shared at times a secretary. Their offices were a couple of doors apart, and into that pressure cooker walked young George Zweig, who would go off to Geneva and come back having found the same thing his rejected advisor found, and get destroyed for it while the advisor got a Nobel. Feynman, for what it is worth, was skeptical of Zweig's Feynman reasoning at first. He thought it violated a principle called unitarity, which is roughly the requirement that probabilities have to add up to one that the books have to balance. This is worth noticing, because it means that even the people closest to Zweig even the mentor who would later become his fiercest defender, did not immediately see that he was right. The idea was strange enough that it triggered resistance in everyone, including the greatest physical intuition of the 20th century. That is how far outside the acceptable Zweig was standing. He wrote it up in Geneva in early 1964, and he wrote it up twice. The first version is a CERN preprint catalogued under the number 8182, dated the 17th of January, 1964. The second version, the big one, is CERN report number 8419, dated the 21st of February 1964, and it runs to about 80 pages. The title of both, and I want you to hear how modest it is, how much it undersells what is inside, is ANSU 3, Model for Strong Interaction Symmetry and its Breaking. That is the document. That is the 80-page manuscript that correctly laid out the constituent structure of all matter, sitting in the CERN system under a catalogue number, with a title so dry you would walk right past it. And Zweig wanted to do the normal thing that any physicist does with a result like this. He wanted to publish it in a proper journal, where it would be refereed and archived and read and cited, where it would count. He wanted to send it to the Physical Review, the premier physics journal in the world, based in the United States. He was not allowed to. The head of the theory division at CERN at that time was a Belgian physicist named Leon van Hove, a serious and respected man, and van Hove would not permit Zweig to submit the paper to the Physical Review. The reason he gave, by Zweig's own account of the conversation, was a matter of policy. All reports coming out of CERN, van Hove told him, had to be published in European journals. CERN was Europe's laboratory, built to establish European physics as a rival to American dominance, and there was institutional pressure to keep CERN's output in European venues, rather than sending the best work across the Atlantic to the Americans. So Zweig's paper, the most important thing he would ever write, was caught in a bureaucratic crossfire about scientific nationalism that had nothing to do with whether the physics was correct, and it did not stop at policy. When Zweig, trying to move things forward, asked the theory division's secretary, a woman he refers to as Madame Faberg, to retype the manuscript so it could be prepared for submission, she refused, not out of malice of her own. She told him that van Hove had instructed her not to type any of Zweig's papers. Let that sit for a moment. The head of the division had gone to the secretary and told her, specifically, do not type this man's work. That is not a policy disagreement about which journal to use. That is a targeted act. That is a man in a position of power reaching down to the level of the typewriter to make sure a specific idea did not get out cleanly. And then there was the seminar. Zweig had scheduled a talk to present the ACES model to his colleagues at CERN, the ordinary way that a physicist announces a new idea and subjects it to questions. He had given it that title, Dealer's Choice, Aces Are Wild, which tells you he still had his humour, still had some spring in his step, still thought he was about to show the room something remarkable. Van Hove cancelled the seminar. It was never rescheduled. Zweig later described the whole pattern in a single devastating sentence. He said that van Hove deliberately and systematically tried to keep his work from public view. Deliberately, systematically, those are not the words of a man describing bad luck or bureaucratic friction. Those are the words of a man describing a campaign. Now, I have to be honest with you about something, because this channel does not traffic in tidy villains, and if I let van Hove become a cartoon, I am lying to you. We only have Zweig's side of these specific conversations. Van Hove is not here to give his. It is possible that from van Hove's chair, this looked like an overeager young postdoc pushing a wild, possibly embarrassing idea about fractionally charged particles, and a division head trying to protect the reputation of his group and his laboratory from associating itself with something that might turn out to be nonsense. That is the charitable reading, and I want you to have it, because it is probably close to what Van Hove believed he was doing. But here is why the charitable reading does not actually rescue anyone. It makes it worse. Because if Van Hove was not a villain, if he was just a reasonable man protecting his institution's reputation, then what buried George Zweig was not evil. It was normal. It was the ordinary, everyday, rational functioning of a scientific institution doing exactly what scientific institutions do, which is to protect themselves from ideas that are too far outside the acceptable, regardless of whether those ideas are true. And a system that buries true things as a matter of routine without anyone ever intending to is far more frightening than a single bad man, because you cannot fire it, you cannot expose it, it is just how the thing works. While all of this was happening to Zweig in Geneva, 3,000 miles away the other version of the idea was gliding effortlessly into the record. Murray Gell-Mann wrote his version up as a 2-page paper. 2 pages. 8 paragraphs. He titled it A Schematic Model of Baryons and Mesons, and he submitted it. And it was received on the 4th of January, 1964, and published on the 1st of February, 1964, in a journal called Physics Letters. And here is a detail that I love because of how much it reveals. Gell-Mann did not send his Quark paper to the Physical Review either. He sent it to Physics Letters, a European journal. And the reason he sent it there was that he thought the Physical Review's letters section might reject it. He was hedging his bets on placement because he too sensed the idea was risky. The difference is that nobody stopped him. There was no division head standing over Gell-Mann telling a secretary not to type his work. Gell-Mann made his own cautious choice about where to publish, and the paper went out into the world under his name. And it was done, and the clock of history started running with his name on it, and not Zweig's. That 2-page paper is where the word comes from. The word you know. The word that beat aces so completely that you have probably never heard the word aces until today. Gell-Mann called his particles quarks. And the story of that word is itself a small perfect example of how history rewards the winner and grooms the story afterward. The common telling is that Gell-Mann took the word from a line in James Joyce's novel Finnegan's Wake, the line 3 quarks for Muster Mark. And that is true, but it is not the whole truth, and the whole truth is more revealing. By Gell-Mann's own account, in a letter he wrote to the editors of the Oxford English Dictionary years later, he had the sound first. He had been using the sound quirk rhyming with cork as a nonsense name for the particles before he ever connected it to Joyce. Then, he came across the word quark on the page in Finnegan's Wake, spelled the way it is spelled, and decided the spelling was too good to pass up, that 3 quarks matched his 3 particles perfectly, even though Joyce almost certainly meant the word to rhyme with mark, not with cork. So the beautiful literary origin story, the erudite physicist pulling his name from the densest novel in the English language, is real but slightly staged. He liked the sound, found the spelling later, and kept the literary pedigree because it was elegant. That is not a crime. It is just a reminder that the winner gets to have a beautiful origin story attached to his word, and the loser does not get a word at all. Zweig had aces, a card metaphor, playful and physical and honestly a little easier to picture, and aces lost. And it lost so thoroughly that its own inventor's name faded with it. And I want to stop here and be fair to Murray Gell-Mann, because it would be easy, given everything I am telling you, to turn him into the villain of this story, and he was not the villain, and the truth about him is more interesting than a villain would be. Gell-Mann was, by almost any measure, the most dominant theoretical physicist of his generation, a man of genuinely staggering range. He did not just do physics, he was a serious amateur linguist who could discourse on the deep history of language families, a naturalist who could identify birds by their calls, a collector of knowledge so voracious and so precise that colleagues found him intimidating to talk to about almost anything, because he probably knew more about it than they did, and would tell them so. The name Eightfold Way, the name Quark, the strange whimsical vocabulary he draped over the deeper structures of matter, all of it came from the same restless, erudite, slightly performative mind. He was the real thing. His contributions to physics were vast, and they were his own, and nothing about the Zweig story diminishes them. But the very thing that made Gell-Mann great is also the thing that shaped how this went, and it is worth naming precisely, because it is the human hinge the whole tragedy turns on. Gell-Mann could not stand to be wrong, not in the ordinary way that everyone dislikes being wrong, but at the level of identity, of self-conception. He was the man who knew about everything, and a person built that way learns to protect himself, to leave escape routes, to say the careful thing rather than the exposed thing. And that instinct is exactly what produced the hedge. When Gell-Mann looked at the fractional charges and felt the danger in them, his lifelong reflex kicked in, the reflex that had made him great, the reflex to never be caught out. So he wrote the sentence about the quarks maybe being purely mathematical, and he built himself the door, because a man who cannot bear to be wrong does not walk into a room and stake everything on fractionally charged particles being real when they have never been seen. He hedges. It was not cowardice. It was the same caution that had made him the most reliable theorist alive, the man whose predictions kept coming true, applied to a case where caution happened to be the thing that let him survive an idea that destroyed the man who believed it fully. There is a rivalry hiding underneath all of this too, and it is the reason the atmosphere at Caltech was what it was. Gell-Mann shared his floor with Richard Feynman, and the two of them were the two most famous physicists in America, and they did not get along in the easy way. They competed, they needled each other. Feynman was the showman, the intuitive, the man who trusted his gut and did not much care about being precise in his citations of other people's work. Gell-Mann was the scholar, the systematizer, the man who cared enormously about precision and priority and getting the names and the credit exactly right. And into that specific rivalry, that specific pressure system, walked young George Zweig, who had been turned down by Gell-Mann as a student and taken in by Feynman, and who then went off and independently found the thing Gell-Mann was building his legacy on. You could hardly design a situation more precisely calibrated to make Zweig invisible. He was the wrong student, from the wrong office, with the wrong version of the right idea, the concrete version, the one Gell-Mann had specifically declined to commit to and specifically called blockheaded. Everything about where Zweig stood in the social geometry of that building pointed toward his erasure. And here is the part that I think is genuinely tragic, rather than merely unfair. The part that keeps me from hating Gell-Mann even a little. In his later years, Gell-Mann himself seemed to come around, slowly, to the concrete view, to the recognition that the quarks were real after all, that the hedge had been a hedge, and reality had gone the other way, Zweig's way. He lived long enough to see the quarks confirmed beyond any doubt, to see quantum chromodynamics built on top of them, to watch the real physical dynamical picture win completely. He got the Nobel, he got the word, he got the history, and he also got to watch the specific man he had called blockheaded turn out to have been more right than he was on the one question that separated them. I do not know what that felt like from the inside. Neither of them ever really said. But it means the story does not have a clean villain and a clean victim. It has two brilliant men who found the same buried truth, one of whom protected himself and won everything, and one of whom exposed himself and lost almost everything, and the difference between their fates came down not to who was right. because on the deepest point, the loser was right. But to who was willing to be careful? The universe rewarded the careful one with a legacy, and the brave one with an unpleasant aftertaste. That is not a morality tale, that is just how it went. Therefore, we have arrived at the situation as it stood in early 1964. Two men, the same discovery, and already a fork. One paper published under one name, clean, quotable, with a word from Joyce attached. One 80-page manuscript trapped in a CERN filing cabinet, its author forbidden to send it to the journal he wanted, its typing refused, its seminar cancelled. If the story ended here, it would already be an injustice worth telling. But it does not end here, because when Zweig left CERN and came home to America, he discovered that the resistance was not a European problem, or a Van Hove problem, or a bureaucratic problem about which journal gets the credit. He discovered that the resistance was everywhere, and in America it stopped being about policy and became something colder and more personal, something aimed not at his paper, but at him. Here is the sentence that George Zweig wrote about it himself, and I want to give it to you in close to his own words, because the restraint in it is more damning than any accusation I could make. Writing years later, looking back, he described the moment his career hit the wall. When the physics department of a leading university was considering him for an appointment, their senior theorist, a man Zweig describes as one of the most respected spokesmen for all of theoretical physics, blocked the appointment at a faculty meeting by passionately arguing that the ACE model was the work of a charlatan. A charlatan. Sit inside that word for a moment, because it is a very particular kind of insult. A charlatan is not someone who is merely wrong. Physics is full of people who are wrong, and being wrong is respectable. It is the ordinary cost of doing science at the edge. A charlatan is a fraud. A charlatan is someone who knows he has nothing and sells it anyway, who dresses up empty nonsense in the costume of real work to deceive people. To call a young physicist's model the work of a charlatan is not to say the physics is mistaken. It is to say the man is a con artist. It is an attack on his character, delivered in a closed room to the people who held his future in their hands, and it worked. He did not get the job. Now I have to stop you before you do the thing everyone wants to do here, which is to demand the name. Who said it? Which university? And I have to tell you something that is more interesting than any name would be. Zweig never said. In his written account, he deliberately kept both the man and the institution anonymous. And in the 60 years since, no historian, no biographer, no journalist has ever authoritatively named either one. There are guesses floating around the internet, confident sounding attributions that people repeat, and I'm not going to launder any of them by repeating them here, because none of them is sourced to anything solid, and passing off a guess as a fact is exactly the kind of thing this channel exists to refuse to do. The name is not known. Anyone who tells you they know for certain who called George Zweig a charlatan is telling you something they cannot support. And I actually think the anonymity is the more terrifying version, because a name would let you make it about one bad individual, one villain you could hate and dismiss as an aberration. The anonymity forces you to confront the real situation, which is that this was not one man. This was the ambient temperature of an entire field. It could have been any number of the most respected theorists alive, because the contempt was general. The idea of real, fractionally charged, physically existing constituents of matter was so offensive to the sensibilities of 1960s theoretical physics that a leading spokesman for the whole discipline could stand up in a faculty meeting and call its proponent a fraud. And the room agreed with him, and the young man's career took the hit. And this was considered normal professional behaviour. It was not only strangers either. When Zweig came back to Caltech and described his model to Gell-Mann himself, the reaction he got from the man who had independently found the exact same thing was, in Zweig's recollection, dismissive in a way that still stings across the decades. Gell-Mann called it, and I am quoting Zweig's memory of the phrase, the concrete quark model, and said that is for blockheads. The concrete quark model, meaning the version where the quarks are real, concrete, physical objects, as opposed to Gell-Mann's own carefully hedged version where they might be only mathematics. That was for blockheads. So the very feature that distinguished Zweig's work, the courage to say these things are real, was thrown back at him as stupidity by the one person on Earth best positioned to understand that he was right. I do not think Gell-Mann was being cruel for its own sake. I think Gell-Mann genuinely believed, or at least professionally needed to believe, that treating the quarks as real was the naive move, the move that would get you burned. But whatever the motive, the effect is the same. Everywhere Zweig turned, from a division head in Geneva to an anonymous grandee at an American university to the co-discoverer in the next building, the message was identical. Say it is only mathematics, and you may pass. Say it is real, and you are a blockhead, or worse, a charlatan. And this is the part where I need to widen the lens, because if you think this pattern is unique to Zweig, you are giving physics far too much credit, and you are missing the reason this story matters beyond the fate of one man. The pattern of a correct idea being strangled because it was uncomfortable is not a one-time failure in the history of physics. It is a recurring feature, and once you start counting the instances, the count becomes hard to stop. David Bohm, in 1952, produced a complete, mathematically consistent, alternative interpretation of quantum mechanics. A hidden variable theory that did everything the standard version did, and for his trouble he was not so much refuted as exiled. His passport eventually caught up in the paranoia of McCarthy-era America, his ideas dismissed with a wave by the priesthood. John Bell, who in 1964, the very same year as the Aces, proved one of the deepest theorems in the history of physics about the nature of reality, spent his career doing that work almost as a hobby on the side, because the questions it addressed were considered unprofessional, not the sort of thing a serious physicist should waste time on. There is a pattern here, and the pattern has nothing to do with the quality of the physics. Bohm exiled, Bell sidelined. Zweig called a charlatan. Over and over, the field's response to someone touching a truth that was too strange was not to engage with the truth, but to punish the person for the discomfort. 1964 alone gave us Bell's theorem being treated as an eccentric hobby and Zweig's aces being locked in a drawer. Two of the most important results of the decade, both filed under unprofessional, both by the same institution that would later teach them as gospel. I promised you a thread at the very beginning, and I need to pull on it here, because we have now built enough for it to start to matter, and I want it to start unsettling you well before we arrive at the bottom. Remember what made Zweig a charlatan in their eyes. He said the aces were real, physically real, findable in principle, actual objects inside the proton. That is the claim that got him destroyed. Now here is the thing I want you to start carrying. Zweig was right that they are real. Completely right. But the specific way in which they turned out to be real is stranger than either Zweig or his tormentors imagined, because the aces turned out to be real objects that can never, under any circumstances, be found alone. Zweig said they exist inside the proton. He was right. But nature added a condition that nobody saw coming. A condition that means you can spend the entire future of the human species building bigger and bigger machines, and you will never, not once, isolate a single one and hold it up to the light. They are real, and they are permanently hidden, both at once, and the reason for that is going to turn out to be the darkest and most beautiful thing in this whole story. Keep it with you, we are not there yet. But it is coming, and the man who was called a charlatan for insisting these things were real would spend no small part of the rest of his life haunted, I think, by the fact that the reality he fought for is a reality no one will ever be permitted to see directly. And there is a reason for the contempt that goes deeper than the fractional charges, deeper than Millikan and the sacred indivisible unit, and almost nobody tells you about it, and it is the single most important piece of context for understanding why Zweig was treated as a fraud rather than merely as a colleague with a bold idea. To understand it, you have to understand what the fashionable theory of the strong interaction actually was in the early 1960s. The idea that the smartest and most prestigious people in the field had staked their careers on, because Zweig's aces did not just contradict a fact about charge, they contradicted an entire philosophy of what physics was allowed to be. The reigning program was called S-matrix theory, and its most influential champion was a physicist named Geoffrey Chew at Berkeley. And its guiding principle had a name that tells you everything: nuclear democracy. The idea of nuclear democracy was that none of the 100-plus particles in the zoo was any more fundamental than any other. There were no building blocks. There was no bottom. Every particle in this view was made up of all the other particles. In an infinitely self-referential web, where each thing was composed of the things that were in turn composed of it, a great democratic bootstrap in which nothing was elementary, and everything held everything else up by mutual consent. It sounds like philosophy, because in a sense it was, but it was serious, mathematically sophisticated physics. And for a stretch of years in the early 60s, it was the most fashionable and prestigious research program in the entire field. The brightest young theorists went into it. It was where the status was. Now look at what George Zweig walked in and said. He said the exact opposite. He said there are building blocks after all. He said there is a bottom, and here it is, 3 of them, 4 of them, real physical objects with fractional charge, and every particle in your democratic web is actually just a different arrangement of these few fundamental cards. He did not just violate a fact about electric charge, he committed heresy against the reigning ideology of the field, an ideology that had explicitly, proudly, as a matter of foundational principle, denied that anything like his aces could exist. Proposing fundamental constituents in the age of nuclear democracy was not like proposing an unusual answer. It was like walking into a cathedral and announcing that the central doctrine was wrong. Of course they called him a charlatan. From inside the bootstrap, a man selling fundamental building blocks was not doing physics at all. He was doing something naive, something the field had supposedly grown out of, something for blockheads, to borrow the word that came back at him from the office next door. And here is the friction. Here is the part that should make you furious on his behalf and skeptical of every fashionable consensus you will ever be handed. Nuclear democracy was wrong. The bootstrap, the whole prestigious edifice, the thing the smartest young theorists poured their careers into, quietly collapsed over the following decade as the constituent picture won. There are building blocks. There is a bottom. The naive, unfashionable, block-headed idea that a young man got called a fraud for proposing turned out to be simply true, and the sophisticated, prestigious, high-status idea that made his proposal look ridiculous turned out to be a dead end. This happens more often in physics than anyone likes to admit. The fashionable thing is fashionable precisely because the prestigious people believe it, and the prestigious people are exactly the ones with the most invested in not being wrong, which makes them exactly the ones most likely to call an outsider a charlatan for seeing what they cannot afford to see. Zweig was not just up against Millikan's quantized charge. He was up against the career investments of the most powerful theorists of his generation in an idea that said his idea could not be right. That is a much bigger wall than a fact. That is a wall made of other people's reputations, and it is the hardest wall there is. But before we get to the hiding, we have to get to the finding, because the aces did not just quietly turn out to be right in some abstract theoretical sense. They were found. Or rather, the evidence for them was found in one of the most important experiments of the 20th century, and the story of that experiment contains its own quiet injustice, its own moment where the credit flowed in a direction that had very little to do with who deserved it. And to see that clearly, you have to go to a 2-mile-long machine in California and watch physicists fire electrons into protons and get an answer that nobody expected and almost nobody wanted. Because here is what everyone expected in the middle of the 1960s if you fired something into a proton. The dominant picture of the proton, held by most serious physicists, was that it was a soft, mushy, uniform blob, not a thing with parts inside it, not a little bag containing 3 hard marbles, a smooth pudding of charge and matter with its properties smeared out evenly through its volume. This picture had a name and a following, and it was the respectable thing to believe. And the reason it was respectable is precisely that it did not require you to believe in Zweig's aces or Gell-Mann's quarks as real objects. A smooth proton has no hard little pieces inside it, so there is nothing embarrassing to explain, no fractional charges to find, no charlatan's marbles rattling around. The mushy proton was the comfortable proton. It was the proton that let everyone avoid the uncomfortable question. Therefore, when they built the machine that could finally look inside, most people did not expect to see marbles. They expected to see pudding. And what the machine showed them was not pudding. The machine sits in the hills south of San Francisco at the Stanford Linear Accelerator Center, and it is 2 miles long. 2 miles. It is one of the straightest objects ever built by human beings. A tube running arrow straight for more than 3 kilometers under the California ground, and its job is to take electrons and accelerate them to enormous energies, up around 20 billion electron volts, and slam them into a target. Electrons are useful for this because they are, as far as anyone can tell, truly fundamental. They have no parts. They are perfect little points of charge. So when you fire a point at a target and watch how it bounces, you are asking the target a very clean question about its internal structure, because you know the thing doing the probing is structureless. Whatever complexity shows up in the bounce belongs to the target, not the probe. The experiment they ran is called deep inelastic scattering, and the word deep is doing real work in that phrase. They were not gently grazing the protons. They were firing electrons hard enough, at high enough energy, to punch deep inside the proton structure and see what was really in there. The team was led by 3 men whose names you should know, because they did the work that proved the charlatan right. Jerome Friedman, Henry Kendall, Richard Taylor. Working through the late 1960s, firing electrons into hydrogen, which is the simplest target there is, because the nucleus of a hydrogen atom is just a single proton, and carefully measuring how the electrons came back out. Now here is the expectation, and you have to hold the expectation clearly in your mind or the result will not land. If the proton is a soft uniform pudding, a smooth smear of charge, then a fast electron fired into it should mostly pass through with only small deflections. Think of firing a bullet into a bank of fog. The fog is soft and uniform, so the bullet barely bends, sailing through with a tiny nudge. You would almost never see a bullet come ricocheting back at a steep angle, because there is nothing hard in fog to ricochet off. That is what the mushy proton believers expected. Lots of gentle forward scattering, almost no hard large angle bounces. That was the prediction, and it was the safe, comfortable, quark-free prediction. And it was wrong. What Friedman, Kendall and Taylor found was that far more often than anyone expected, the electrons came ricocheting back at large angles, sharp, hard deflections, as if they had struck something small and solid deep inside the proton and bounced off it violently. The proton was not fog. There were hard little things in there. Points, and when the results were first shown at the Great International Physics Conference in Vienna in 1968, they were a genuine shock because they meant the comfortable picture was finished. The proton had structure, it had constituents, it had, whether anyone liked the word or not, marbles inside it. There is a beautiful historical rhyme buried in this, and I cannot resist it. The whole thing is almost exactly the same experiment, in spirit, that Ernest Rutherford's team ran in 1911 when they fired alpha particles at gold foil and found, to their astonishment, that some of them bounced straight back, which meant the atom was not a smooth pudding either, but had a tiny hard nucleus at centre. Rutherford said it was as if you had fired a 15-inch artillery shell at a sheet of tissue paper and it had come back and hit you. 60 years later at Stanford, the same shock happened one level deeper. Fire something into the proton, expect it to sail through, and instead it bounces off hard little points inside. The universe, it turns out, keeps the same secret at every scale, and the secret is that the smooth things are never actually smooth. There is always another layer of hard little somethings underneath, hiding, waiting for someone to build a machine big enough to bounce off them. The person who worked out what the hard points meant was, of all people, Richard Feynman, Zweig's own advisor, the man who had initially been skeptical of the whole thing. Feynman came up with a way of thinking about the proton as a collection of small, nearly free-point particles, which he called partons, from the word parts. He was cautious about identifying them with quarks at first, keeping his own careful distance, the way physicists did. But the parton picture explained the SLAC data with beautiful precision, and it did not take long for the field to make the connection that the partons and the quarks and the aces were all the same thing. The hard points inside the proton that were scattering the electrons at Stanford were exactly the constituents that Zweig had said were real, and that a leading theorist had called the work of a charlatan. The marbles were there. They had always been there. And now a 2-mile machine had felt them. For this work, Friedman, Kendall and Taylor won the Nobel Prize in Physics in 1990. And that prize is completely deserved, and I have no quarrel with it whatsoever. They did superb, careful, decisive experimental work, and they earned every bit of the recognition. I raise it only to draw the contrast that this whole story keeps drawing, which is that the machine that proved Zweig right got a Nobel, and the theorists who later explained the deep behaviour of the constituents would get a Nobel, and the experimenters who found the fourth ace would trigger a revolution, and through all of it the man who said, first and clearly, and at great personal cost, that these things are real, watched the prizes go out to everyone around the idea, while the central credit for the idea itself settled on one name, and that name was not his. And there is one more piece of vindication I have to give you before the prize, because it is the cleanest proof that Zweig's version, the real version, the concrete version that got cold, blockheaded, was doing something Gell-Mann's careful hedge could never do. It has to do with magnetism, and it is the kind of quiet, specific, decisive result that should have ended the argument on its own, and instead got filed away as a curiosity. Every particle that carries charge and spin acts like a tiny magnet, with a strength that physicists call its magnetic moment. The proton has one. The neutron, despite being electrically neutral overall, also has one, which is already a hint that the neutron has charged parts inside it arranged in some structured way, because a truly neutral featureless blob would have no magnetic moment at all. Now, if you take Zweig's version seriously, if you say the proton and the neutron are not smooth objects, but are literally, physically, 3 real spinning quarks each, then you can do something the mathematical hedge cannot do. You can calculate. You can add up the magnetic moments of the 3 little spinning charged quarks inside the proton and the 3 inside the neutron, treating them as real objects with real spins and real charges, and predict the ratio between the proton's magnetism and the neutrons. The concrete quark model makes a sharp prediction. It says the ratio of the proton's magnetic moment to the neutrons should be about -3/2, -1.5. That is a specific number that falls out of taking the quarks literally as real physical spinning things. And when you go and measure the actual ratio in the real world, the answer is about -1.46. The prediction and the measurement agree to within a couple of percent. A theory that most of the field considered too naive to take seriously, built by treating as concrete physical objects the very particles that the sophisticated people insisted were probably just mathematics, walked up and predicted a fundamental property of the proton and the neutron to within a few percent. From almost nothing, from just adding up the pieces. Think about what that means in the context of everything we have said. The distinguishing feature of Zweig's approach, the thing that got him called a charlatan, was that he treated the quarks as real. Gell-Mann's hedge, the escape route that kept him respectable, was to say they might be only mathematical, but you cannot calculate a magnetic moment from a mathematical convenience. To get that number, that -1.5 that matches reality so beautifully, you have to commit. You have to say these are real objects, they really spin, they really carry these charges, and their real magnetism really adds up. The prediction only works in Zweig's world, the concrete world, the blockheaded world. The careful agnostic version cannot even ask the question, because to ask it you have to believe the quarks are the kind of thing that has a magnetic moment, which is to say you have to believe they are real. The magnetic moment result is not just evidence that quarks exist, it is evidence that the specific man who insisted they were physically real and got destroyed for it had hold of the correct picture, and the specific man who hedged and stayed safe had, on this exact point, been protecting himself rather than following the physics. And it was treated as a footnote, a nice result, a curiosity, a thing you mention in passing, not the vindication it actually was. Because by the time these numbers were being appreciated, the story had already set. The credit had already flowed, and a magnetic moment ratio matching to 2% was not going to unset it. This is how it goes when the narrative has already chosen its hero. The evidence keeps arriving, piece after piece, each one pointing at the man who was written out, and none of it is enough to rewrite the story, because stories are not rewritten by evidence. They are rewritten by attention, and nobody with the power to redirect the attention had any incentive to do so. Which brings us to the prize, the big one, the one that everybody remembers, and to the single cleanest piece of evidence that the field had decided how this story would be told. In 1969, the Nobel Prize in Physics was awarded to Murray Gell-Mann, a lone no co-recipient, for his contributions and discoveries concerning the classification of elementary particles and their interactions. Read that citation carefully, because there is something strange hiding in it. It does not mention quarks, not once. In 1969, the quark model was still too controversial, too unproven, too tangled up in the embarrassing question of whether those fractional charges were real, for the Nobel Committee to be willing to stake the prize on it directly. So they gave Gell-Mann the prize for the Eightfold Way, the safe classification work, the periodic table part, and they left the quarks pointedly out of the official language. The prize was, in a sense, awarded for the part of Gell-Mann's work that did not require anyone to believe in the dangerous idea. But the effect on history was total anyway. Gell-Mann had a Nobel Prize. Gell-Mann had the word quark, which was busy conquering the language. And George Zweig had an unpublished CERN report, a memory of being called a charlatan, and the private knowledge that he had found the same thing. The prize did not name the quarks. but it crowned the man, and the crown settled the story. When people wanted to know who discovered the quark, there was now an obvious answer with a medal attached, and the obvious answer did not require anyone to go digging in the CERN archive for an 80-page manuscript by a man who had left for the office next door. You will sometimes hear it said that Zweig could not have shared the credit or the prize because his work was never formally published in a journal, only circulated as an internal CERN report, and that this technicality disqualified him. I want to correct that, because it is a rationalization dressed up as a rule. The requirement when it comes to recognizing scientific priority is essentially that the work be made public, that it exist and be available and be datable. Zweig's reports exist. They are dated. They circulated. Physicists at the time knew about them. The claim that a lack of formal journal publication cleanly disqualifies the work is not a neutral fact of the rules. It is a way of making the outcome feel inevitable, of laundering a series of human choices, Van Hove's refusal, the secretary's instructions, the cancelled seminar, the charlatan's speech, into a tidy procedural technicality that lets everyone off the hook. The reason Zweig's work was only an internal report in the first place is that he was forbidden to publish it properly. To then turn around and disqualify him because it was only an internal report is to punish him twice with the same act. First, we will stop you from publishing. Then we will exclude you because you did not publish. That is not a rule. That is a trap. And the cruelest detail, the one that I keep coming back to, is who tried to fix it. Richard Feynman, Zweig's old advisor, the man who had been skeptical at the start, came to understand exactly what had happened and exactly how unjust it was. And in 1977, Feynman formally nominated both Gell-Mann and Zweig for the Nobel Prize. Together, for the quark, he was trying to put Zweig's name back into the story at the highest possible level to force the recognition that the field had withheld. The nomination did not succeed. There was no shared Nobel for the quark. But the gesture tells you everything, because of a detail Zweig himself pointed out afterward with obvious emotion. He said that Feynman, to his knowledge, never nominated anyone for anything. Feynman was not a man who lobbied for prizes or played the recognition game. And yet Feynman went out of his way, broke his own habit of a lifetime, to try to get George Zweig the credit he had earned. Zweig called it a real tribute, and you can hear in those words a man clinging to the one piece of vindication he actually got, which was not a prize, and not a word in the dictionary, but the private knowledge that Richard Feynman thought he deserved one. Meanwhile, the aces kept proving him right, kept vindicating the buried document, and one of those vindications is worth pausing on because it goes to the deepest thing about how Zweig thought. Remember that he called them aces, plural, 4 of them, even though his working model used 3, and remember why. He suspected there had to be a 4th, and his reasoning was a kind of intuition about symmetry between the constituents of matter and another family of particles called leptons, the family the electron belongs to. There were 4 known leptons at the time, and Zweig guessed that the number of aces should match the number of leptons, that nature would want them to balance. It was a hunch about a particle that had never been seen and that most people had no reason to expect. And on the 11th of November, 1974, that 4th ace announced itself. 2 teams, one led by Samuel Ting at Brookhaven on the East Coast, and one led by Burton Richter at Stanford on the West Coast, discovered the same new particle at almost the same moment. A discovery so sudden and so consequential that physicists still call it the November Revolution. The particle, which they named with 2 letters because the 2 teams had 2 different names for it, revealed the existence of a 4th quark, the one now called Charm. Zweig's 4th ace, His hunch about balancing the leptons was correct. The card metaphor, the deck of 4, had been physically right all along. Ting and Richter shared the Nobel Prize for that discovery in 1976. And I want you to notice the shape of the ledger we have built. A Nobel for the Eightfold Way to Gell-Mann. A Nobel for finding the constituents at SLAC to Friedman, Kendall and Taylor. A Nobel for the November Revolution that confirmed the fourth ace to Ting and Richter. Prize after prize after prize, orbiting the idea that George Zweig had co-discovered and been called a charlatan for, and not one of them with his name on it. The idea was among the most decorated in the history of physics. The man was not decorated at all. He was, by then, already halfway out the door of the field entirely. Because there is only so long a person can watch the world celebrate his idea while pretending he had nothing to do with it before he decides to go find something else to do with his mind. And what he went and did with his mind is one of the strangest third acts any physicist has ever had, and it circles back. In a way I do not fully know how to describe, to the very thing he had discovered. George Zweig walked away from particle physics, not in a dramatic slam door way, but steadily, decisively, in the manner of a man who has looked at the terms of the game and quietly declined to keep playing. He would later describe the state of high-energy physics, the field he had helped to found, in a phrase that I find almost unbearably sad in its precision. He called it locally exciting, but globally disappointing. Read that the way an engineer's son would mean it. Locally exciting means that up close, day to day, there is always some clever result, some new particle, some conference with something to argue about. Globally disappointing means that when you step back and ask whether the whole enterprise is going anywhere that matters, whether it is deepening in the way it once promised to deepen, the honest answer is no. He had been present at the single most important moment the field would ever have, the moment it found what matter is made of, and he had been treated as a fraud for it. And now he was telling you that the rest of it, viewed from a great enough height, was not worth a life. That is a devastating thing for a founder to say about his own field, and what he did instead is the detail that turns this from a story about injustice into something closer to a parable. Because George Zweig, the man who had discovered the hidden constituents of matter, left physics to go study the inside of the human ear. Specifically, he went into neurobiology, and he became fascinated by the cochlea, the tiny spiral organ in your inner ear that takes the pressure waves of sound and turns them into the electrical signals your brain can actually use. He wanted to understand the transduction of sound, the exact mechanism by which a vibration in the air becomes a perception in a mind. Think about the shape of that move for a second. He had spent his early career on the question of what things are made of, on the hidden hard reality underneath the smooth surface of matter. And he pivoted to the question of how the hidden hard reality of the world gets translated into the soft surface of experience. How the vibrations that are really out there become the sounds that seem to be in here. He went from the constituents of matter to the constituents of hearing, from what the universe is to how a person perceives it. And in the course of that work, in the mid-1970s, he did something that would have made him famous in an entirely different field if his name were the kind of name that got attached to things, which by now you understand it is not. Studying how the cochlea analyzes sound, breaking a signal down into its component frequencies the way the ear does, Zweig worked out a piece of mathematics that is essentially a version of what is now called the continuous wavelet transform. Wavelets are a mathematical tool for analyzing signals at multiple scales at once, for zooming in and out on the structure of data, and they became, in the decades after, one of the most important techniques in all of applied mathematics and engineering. They are used in image compression, in signal processing, in the analysis of everything from earthquakes to medical scans. When you look at certain kinds of digital images, you are looking at the fruit of wavelet mathematics, and a version of it fell out of George Zweig trying to understand your ear. The man could not stop discovering foundational things. He just kept doing it in fields where nobody was watching for a physicist's name. The recognition he did get in his life tends to come from these later, quieter directions, which is its own kind of comment. He was named to the very first class of MacArthur Fellows, the so-called Genius Grants, in December of 1981, when the foundation handed out its inaugural awards to a group of people it considered exceptionally creative. He was elected to the United States National Academy of Sciences in 1996. Late in life, in 2015, the physics community did give him one of its significant honours, the Sakurai Prize, a recognition decades overdue, of the theoretical work he had done as a young man. He spent years as a fellow at Los Alamos, the national laboratory born out of the atomic bomb, working on hard problems across disciplines. But you will notice that none of this is the thing. None of it is a Nobel, none of it is a word in the dictionary, none of it is a place in the standard story that every physics student learns. It is the recognition a field gives to someone it respects, but has, in the deepest sense, already written out of its central narrative. And then, in a final turn that I could not have invented, the man who named the building blocks of matter went to Wall Street. In 2003, George Zweig joined Renaissance Technologies, the legendary quantitative hedge fund founded by the mathematician James Simons, a firm famous for hiring physicists and mathematicians to find hidden patterns in the chaos of financial markets. Think about what that work actually is. It is once again the search for hidden structure underneath a surface that looks random and smooth. The markets look like noise, like a smooth mush of prices, and the entire premise of a fund like Renaissance is that there are hard little regularities buried inside the noise, patterns that are really there if you have the mathematics to feel for them. It is the SLAC experiment all over again, at a third level. Fire your analysis into the mushy surface, and find the hard hidden things underneath that nobody else believed were there. Zweig had done it with the proton and been called a charlatan. He did it with the cochlea and invented wavelets, and now he did it with the markets, for a firm that made its investors staggeringly wealthy precisely by believing that the hidden hard structure was real when the efficient market orthodoxy insisted it was only noise. He stayed until 2010. And then, after his confidentiality agreement had run its course, in his late 70s, an age when most people have long since stopped, George Zweig went back to the markets and co-founded a new quantitative fund of his own, with two younger partners, which began trading around 2015. In his late 70s, still looking for the hidden structure, still refusing to accept that the smooth surface is all there is, I find something almost heroic in that, and also something a little heartbreaking. Because you have to wonder what a man like that could have done for physics if physics had wanted him, if the field had championed its charlatan instead of exiling him, if the 80-page document had been welcomed instead of buried. We will never know, because the field made its choice in 1964, and the choice sent one of the great pattern finders of the century off to spend his genius on ears and earthquakes and equity markets, anywhere but the field he had helped to build. There is an idea in the framework I use for thinking about these stories, a recurring pattern where the personal circumstances of a scientist mirror or invert the physics they discovered, and I have been resisting it with Zweig because it seemed too neat, and I no longer want to resist it, because I think it is simply true. Here is the mirror. George Zweig's entire life was defined by barriers. He existed only because a barrier, an immigration gate, happened to open for him while closing fatally on his grandparents. His career was destroyed by a barrier, the wall of institutional refusal that a division head and an anonymous grandee and a co-discoverer's contempt built around his idea. He spent his life either slipping through barriers that should have stopped him, or being stopped by barriers that should have let him through. And the thing he discovered, the ace, the quark, turns out to be the one object in all of physics that is defined, more than by anything else, by a barrier that can never be crossed. The quarks are trapped. They are walled in by a force that will not let them out, a force that gets stronger the harder you pull, a prison with no possibility of escape written into the deepest laws of nature. The man made by Gates, unmade by Gates, discovered the particle that is imprisoned by the most absolute gate in the universe. And it is that gate, that prison, that impossibility, that we finally have to walk all the way into, because it is where this entire story has been heading from the first sentence, and it is stranger than I have let on. So let me tell you what a quark actually is now. The real version. The version that vindicates George Zweig completely, and then adds a twist that makes the vindication feel like a haunting. When Zweig said the aces were real, he was right, and the way we know he was right is not just the SLAC experiment. It is the entire edifice of modern physics, a theory called quantum chromodynamics, which describes how quarks bind together, and which is one of the most precisely tested theories in the history of science. Quarks are as real as anything is real. There are 6 of them now, 6 flavors, up and down and strange and charm and bottom and top, and everything you think of as ordinary matter, every proton and neutron in every atom in your body, is built from the 2 lightest ones, up and down, exactly the way the buried document said. This is not speculative. This is not one interpretation among many. This is the bedrock of what we know. Zweig won the argument about reality so completely that the argument is not even remembered as an argument anymore. And yet no human being has ever seen a single quark alone. Not once. Not in the 2-mile machine at Stanford, not in the 27-kilometer ring at CERN that came later and is the most powerful accelerator ever built, not anywhere, ever, in any experiment. At any energy we have been able to reach. Every quark that has ever existed since the first fraction of a second after the Big Bang has been bound up with other quarks, locked inside a proton or a neutron or some other composite particle, and no quark has ever been pried loose and observed on its own. This is not a limitation of our instruments. This is not a matter of building a bigger machine. This is a feature of the laws of nature themselves, and it has a name. Confinement. Here is why it happens, and I need you to follow this carefully, because it inverts everything your intuition tells you about how forces work. Every force you have ever experienced gets weaker with distance. Gravity gets weaker the farther apart 2 masses are. The electric force gets weaker the farther apart 2 charges are. Move things apart, and the pull between them fades. This is so universal that you probably think of it as simply what a force is. The strong force, the force that binds quarks, does the opposite. When 2 quarks are close together, the force between them is almost nothing, and they rattle around nearly free. Which is exactly why the electrons at SLAC saw them as hard little independent points. That property has a name too, asymptotic freedom, and 3 physicists, David Gross, Frank Wilczek, and David Politzer, worked out the mathematics of it in 1973 and won the Nobel Prize for it in 2004. Another Nobel, you will notice. Orbiting the idea Zweig was called a charlatan for. But here is the part that matters for confinement. As you pull 2 quarks apart, the force between them does not weaken. It stays roughly constant, and the energy stored between them keeps climbing, and climbing without limit, the way the tension in a stretched spring keeps building the more you stretch it. Except this spring never reaches its limit, and never snaps from being overstretched. Picture it as a string, because that is genuinely how physicists picture it. A tube of pure force running between the two quarks, and imagine trying to separate them. You pull, and the string stretches, and the energy in the string rises. You pull harder, pour in more energy, and the string stretches further and stores more energy still. And you might think, if I just pull hard enough, if I just pour in enough energy, eventually I will rip one quark free and hold it in my hand, isolated, alone, the first person in history to see a naked quark. But you never will. Because at a certain point you have poured so much energy into that stretched string that the energy itself, by the most famous equation in physics, the equivalence of energy and mass, becomes cheaper to convert into brand new particles than to keep stretching. And so instead of the string snapping and releasing a free quark, the string snaps and out of the released energy a new quark and a new anti-quark are born in the gap, and they attach themselves to the ends, and now instead of one particle being pulled into two free quarks, you have two particles, each still containing bound quarks, and not a single free quark anywhere. You tried to break the prison, and the prison responded by building more prison. You tried to isolate one, and nature answered by manufacturing company for it, out of the very energy you supplied. I want to use a word here that I try to be careful with, but I think it is earned. It is almost as if the vacuum refuses. You reach in to take one, and reality will not permit the taking, and it enforces the refusal not passively, but actively. Spending your own energy to spawn new matter for the sole purpose of making sure no quark is ever left standing alone. Every attempt to see the thing directly is answered by the creation of more things to hide it behind. The harder you look, the more thoroughly it is concealed. This is not a metaphor I am imposing on the physics. This is what the equations say happens, and it happens every time without exception, and it is why the most fundamental constituents of everything you are made of are the one category of object in the universe that you are forbidden, by law, from ever holding up to the light. Now bring George Zweig back into the room and feel the full weight of it. This is the man who was called a charlatan for insisting these things were physically real, and they are physically real. But the specific reality they possess is a reality of permanent hiddenness. Zweig fought his whole career against a barrier of institutional refusal, a wall of people saying, no, you may not publish this, no, you may not have this job, no, this is not serious, no. You are a fraud. And the particles he discovered live behind a barrier of natural refusal, a wall that says no, you may not see me alone, no, you may not isolate me, no matter how much force you bring, the answer is no. The parallel is so exact it stops being poetry and starts being something closer to a cruel joke told by the universe. The man made of denied entry, unmade by denied recognition, discovered the object that denies observation. His life and his physics are the same shape, refusal all the way down. And I have been holding back the strangest part, the part that takes this out of the laboratory and puts it directly into your own body, because I wanted you to understand confinement first. Here it is. The quarks inside a proton are almost weightless. The two up quarks and one down quark that make up a proton, if you add up their intrinsic masses, account for only about 1% of the proton's total mass. 1%. So where does the other 99% come from? Where does the mass of the proton, and therefore the overwhelming majority of the mass of every atom in your body, actually come from? It comes from the confinement itself. It comes from the enormous energy of the churning, seething field that binds the quarks, the energy of that unbreakable string, converted into mass by the same equivalence of energy and mass that spawns the new particles when you pull. The quarks are nearly massless. The prison that holds them is where almost all the weight lives, which means that you, your body, The physical mass of you, the number on the scale, is not mostly made of stuff. It is mostly made of the binding energy of a force whose defining property is that it will never let you see what it is binding. You are, to the tune of about 99%, the energy of a prison holding particles you can never meet. Sit with the vertigo of that for a moment, because it deserves it. When you knock on a table and it feels solid, when you press your hand against a wall and it stops you, the solidity you are feeling is almost entirely the energy of confinement, the resistance of the strong force refusing to be compressed, refusing to release its captives. The hard reality that stops your hand is not the hardness of little marbles. It is the hardness of a refusal. It is the vacuum saying no. Everything you have ever touched, every solid object that has ever pushed back against your body, was pushing back with the energy of a prison that hides its own prisoners. Zweig discovered the prisoners. He was called a fraud for saying they were real, and it turns out they are so real that they make up the felt solidity of your entire physical world, and so hidden that you will die, and everyone you love will die, and the human species will end, and not one of us will ever have seen a single one of them on its own. And here is the final turn of the screw, the thing that keeps this from being a closed story with a satisfying ending, the thing that should genuinely disturb you if you have followed me this far. We cannot prove that confinement happens. We know it happens. We see it in every experiment every single time with total reliability. But we have never been able to prove it rigorously from the fundamental equations of the theory. The mathematics of why quarks are permanently confined, why the force behaves this way at large distances, remains unsolved. It is not a minor gap. It is considered one of the deepest open problems in all of mathematical physics, so important that it is one of the 7 Millennium Prize problems named at the turn of the century with a $1 million prize attached, and it has never been claimed. The specific problem, called the Yang-Mills existence and mass gap problem, is essentially the demand to prove, from first principles, the thing we already know is true, the thing Zweig's vindication rests on. We are made almost entirely of the energy of confinement. Confinement is the most reliable fact in particle physics, and no one on Earth can prove why it happens. The flaw under everything, the thing that gives you your very mass, is real and hidden, and, at the deepest level, unexplained, you might be waiting at this point for the redemption, for the part where the field realizes what it did and makes it right. And there is a version of that, a partial, late, grudging version, and I want to give it to you honestly, because I am not interested in making Zweig into a purer martyr than he was, or the field into a purer villain than it was. The record did get corrected. Some, just not enough, and not in the place where it would have mattered, which is the place where you learned physics. Murray Gell-Mann in his later years did acknowledge Zweig. If you go and listen to Gell-Mann talk about the history, he will tell you without much fuss that George Zweig developed the same idea independently while he was at CERN, and that Zweig called them aces. He does not deny it. In the small world of people who actually know the history, Zweig's independent co-discovery is not controversial at all. It is accepted. The physicists who care about priority know exactly what happened, and give Zweig his due in the specialist literature and the review articles and the conference talks. There is even a sense among some who have looked closely that Zweig's version was in certain ways the more physical, the more prescient, the more nearly correct about what the quarks actually were, precisely because he insisted they were real objects with dynamics rather than mathematical conveniences. In the community that remembers, he is remembered. CERN itself, the laboratory whose theory division buried his paper, eventually came around to honouring him. In 2013, on the occasion of the 50th anniversary of the Quark model approaching, CERN sat George Zweig down for a long interview and let him tell the whole story. The Van Hove refusal, the secretary who would not type his manuscript, the cancelled seminar, all of it, published under CERN's own name. There is something almost vertiginous about that. The same institution that had spent its authority in 1964 making sure this story stayed hidden, spending its authority in 2013 making sure the story of the hiding got told. 50 years is how long it took for the laboratory to move from suppressing the man to platforming him. 50 years. Zweig was 76 by then. He had had an entire second and third career in the time it took the institution to admit what it had done in his first. But here is the friction, here is the thing I want you to be angry about, because the anger is correct and earned and not manufactured. None of that correction reached you. The specialists know. The review articles are careful. CERN eventually held the door open. And yet the story that propagated out to the world, the story in the popular books, the story in the documentaries, the story that most physics students absorb and most educated people carry around, is still the tidy one. The one where Gell-Mann invented the quark and named it from Joyce and won the Nobel. Full stop, clean, single hero, no charlatan, no filing cabinet, no 80-page document, no George Zweig. The correction happened in the specialist attic and never came downstairs. And this is exactly how erasure actually works in a modern knowledge system. It is not that the truth is destroyed. The truth is preserved, meticulously, in venues that the public never reads. It is simply that the convenient version is the one that gets copied and copied and copied into every textbook and every classroom and every popular account, until the convenient version is the only version that most people ever encounter, and the true version sits perfectly intact in a journal that 99.9% of the human race will never open. The lie does not require anyone to burn the truth. It only requires that the truth be less repeatable than the lie, and a story with one hero is always more repeatable than a story with two, one of whom was wronged, and the field kept finding ways to wound Zweig even after he had left it, which tells you the resistance was never really about the physics. When he made his move into neurobiology when he walked away from particles to go study the ear, one of his own former Caltech professors, a physicist named Robert Christie, reportedly tried to have him fired for it. Think about the message in that. Christie had earlier steered Zweig toward experiment and away from the theoretical work that produced the aces, and now, when Zweig committed the sin of leaving physics for another field, an old mentor tried to end his employment for it. It was not enough that Zweig had been called a charlatan for his best idea. When he tried to go be brilliant somewhere else, the field reached out to punish him for that too. There is a kind of person and a kind of institution that cannot forgive you for being right in a way it did not sanction, and cannot forgive you for leaving, and George Zweig ran into both. Zweig himself, in the rare moments when he wrote about the emotional reality of it, chose his words with a restraint that hurts more than fury would. Reflecting on the reception his model got when he first proposed it, he wrote that the negative reaction of the theoretical physics community had left a lingering, unpleasant aftertaste. An unpleasant aftertaste. That is how a proud and careful man describes being called a fraud for one of the great discoveries of the century, being blocked from a job, being buried by a division head, and watching the credit and the prizes and the word itself flow to everyone but him. Not a scream, not a lawsuit, an aftertaste. Something bitter that never quite left his mouth for the rest of his life underneath everything else he accomplished. And he accomplished so much else, the wavelets and the cochlea and the markets, that you could almost believe the aftertaste did not matter. But he mentioned it. Decades later, with all his other successes behind him, he still mentioned the taste. It mattered. So let me say plainly what this story is actually about, because we have gone deep enough now that I can say it without it sounding like a slogan. This is not a conspiracy. I have said that twice, and I will say it a third time, because it is the crux. Nobody held a meeting to erase George Zweig. There is no cabal, no plot, no smoke-filled room. What there is something worse than a conspiracy, because a conspiracy at least requires that someone intended the outcome and could in principle be held responsible for it. What erased Zweig was 1,000 small, comfortable, individually reasonable choices, each one made by a person who was mostly just protecting themselves. Van Hove protecting his laboratory's reputation, the anonymous grandee protecting his department from an embarrassing hire, Gell-Mann protecting his own hedge by calling the real version blockheaded, the Nobel Committee protecting the prize by keeping it safe, and then every textbook author after them protecting the reader from complexity by telling the simple version, and every documentary protecting the runtime by cutting the second man, and every teacher protecting the class from confusion by naming one discoverer instead of two. Not one of those people was a villain. Almost every one of those choices was defensible on its own terms. And the sum of all those defensible choices is that a man who co-discovered the structure of matter was written out of history and called a fraud along the way, and you, personally, sitting there right now, were handed the version with the hole in it and told it was the whole truth. That is the pattern. And the pattern is not confined to George Zweig, and it is not confined to physics. And the reason it should frighten you is that it does not need bad people to keep running. It runs on ordinary institutional comfort, on the preference for tidy stories, on the fact that the truth is always more complicated and more repeatable lies are always more useful, and on the quiet reality that the people who guard the gates of knowledge are, like the immigration officials who let a Zweig through and turned his grandparents away, just people making choices about who counts, choices that get remembered as facts. You were taught that the history of physics is a meritocracy, that the best ideas win and the best people are honoured and the truth rises because it is the truth. Go read the CERN interview. Go find the 80-page document. Go look at the word charlatan sitting in George Zweig's own careful prose, describing what one of the most respected physicists alive said about him in a closed room, and then tell me it is a meritocracy. I want to take you somewhere colder before we finish, because there is a level of this that goes underneath even the confinement, underneath even the 99% of your mass that is prison energy, and it has to do with when the gates closed. Because the quarks were not always trapped. There was exactly one moment in the entire history of the universe when they were free, and understanding that moment changes how you should feel about the fact that they are not free now. Roll the clock back, not to your birth, not to the formation of the Earth, not even to the birth of the stars. Roll it all the way back to the first fraction of the first second after the Big Bang, somewhere around a millionth of a second in, when the entire universe was so unimaginably hot and dense that the strong force could not hold anything together. In that instant, the cosmos was not made of protons and neutrons. It was made of a plasma, a seething soup of quarks and gluons moving freely, unbound, naked, the only time in all of history that the aces existed the way George Zweig first imagined them, as free particles you could in principle point to one at a time. For a sliver of an instant at the very beginning of everything, the prison did not exist yet. The quarks were loose. And then the universe cooled, by a hair, past a critical threshold, and the gates slammed shut. Physicists call it confinement switching on, or the strong force freezing out, and it happened once, universally, everywhere at once, in the first flicker of time, and it has never once reversed. every quark that was free in that first millionth of a second got captured, bound into a proton or a neutron, locked into a composite object, and it has been locked ever since, for 13.8 billion years. The quarks in your body were free for an instant at the dawn of time and have been imprisoned every single moment since. Through the formation of the first atoms, through the birth and death of generations of stars that forged the heavier elements, through the assembly of the Earth and the emergence of life and the entire history of your species, right up to this exact second in which they are still trapped, still churning, still refusing to be seen, inside you. The window of freedom lasted less time than it takes light to cross a single atom. The imprisonment has lasted the age of the universe and will last until the universe ends. And I have to correct one more comfortable picture, the last one, because I let you keep it too long and it is not true. I told you a proton is 3 quarks, 2 up and 1 down, the way Zweig's Treys said. That is the version in the textbooks, the tidy version, and it is a simplification sitting on top of something much wilder, and by now you should expect that. Because every tidy version in this story has been a lid on something churning. Inside a real proton there are not 3 quarks sitting politely like 3 marbles. There is a boiling, roaring ocean. The 3 quarks people name, the valence quarks, are just the persistent identity of the thing, the net excess. Like the name of a river that is actually made of trillions of individual water molecules that are never the same twice. Around and through those 3, the interior of the proton is a seething storm of gluons, the carriers of the strong force, and of countless quark and anti-quark pairs flickering into and out of existence, borrowing energy from the field and paying it back. A population so dynamic and so uncountable that the question how many quarks are in a proton does not even have a clean answer. It depends on how hard you look. The harder you look, the more you find. A proton is not 3 particles. It is a bottomless, self-renewing, confined ocean that from the outside merely looks like a single stable speck. So when George Zweig said the aces are real, he was not just right in the modest way his tormentors eventually quietly conceded. He was right in a way that outran even his own imagination. He said there were real physical objects inside the proton with mass and spin and dynamics. And there are, and they are more real and more numerous and more violently alive than 3 marbles could ever be, an entire imprisoned sea, boiling inside every particle of you, at every instant, and it has been boiling since the 3rd minute of creation, and you will never see a drop of it. The charlatan was not overselling. If anything, he was underselling. The reality he insisted on and got destroyed for is vaster and stranger, and more permanently hidden than the version that got him called a fraud. He was punished for going too far, and it turns out he did not go far enough. Because the truth went further than he dared, and the truth agreed with his direction every step of the way. That is where the physics leaves us, and it does not leave us anywhere comfortable, and I am not going to pretend it does. Everything solid you have ever known is the felt pressure of a prison. Almost all of your weight is the energy of that prison. The prisoners were free for 1 instant at the beginning of time, and have been captive ever since. There are more of them inside you than can be counted, boiling, and you cannot see even one. And the man who first told the world they were real, plainly and bravely and at the cost of his career, was told, by the people who should have known better, that he was a fraud. The document is still there. That is the thing I keep returning to. The image I cannot put down. The 80-page manuscript, catalogue number 8419, dated the 21st of February, 1964, with its dry, unremarkable title, ANSU 3 Model for Strong Interaction Symmetry and its Breaking, is still sitting in the CERN archive, exactly where it has been for more than 60 years. you can find it. It is preserved, ironically, meticulously, by the same institution whose theory division once refused to let it be typed. It correctly describes what you are made of. It was written by a 26-year-old who had just finished his doctorate, working mostly alone in a foreign country, chasing a small puzzle about a decaying particle, and stumbling instead onto the architecture of all matter. And it was forbidden. The best thing its author would ever write, and he was not allowed to send it where it belonged, and the man who forbade it did so, most likely, not out of malice, but out of the ordinary reasonable instinct to protect an institution from an embarrassing idea. The most important document of a man's life, killed by good institutional judgment. That combination, the importance and the reasonableness of its suppression, is the whole tragedy compressed into a single object you could hold in your hands if the archive let you. George Zweig gave his seminar a name before any of this happened to him, back when he still thought he was about to walk into a room and show his colleagues something remarkable. He called it Dealer's Choice. Aces are wild. There is a version of the universe in which that seminar happened, in which the young man stood up in front of the CERN theory division and laid out the aces and the deuces and the treys, the whole hand, and the room understood what it was seeing, and the credit fell where it belonged. And today you would learn the names of 2 discoverers instead of 1, and the word for the building blocks of matter might have been aces, a card metaphor, playful and physical, instead of a sound borrowed from a novel almost nobody has read. That universe did not happen. The seminar was cancelled and never rescheduled. Aces are wild, but the dealer never got to deal because the man who ran the table took the cards away before the hand could be played. And the deepest cut, the one I have been circling this whole time, is that the reality he was reaching toward turned out to be built on exactly the kind of refusal that defined his life. He was made by a gate that opened for him and closed on his grandparents, who died at Riga in the winter of 1942 while he was a small child safe in Detroit because 2 senators happened to intervene. He was unmade as a physicist by a gate of institutional refusal, a division head, and an anonymous grandee, and a co-discoverer's contempt. A wall of no that he could never quite get through. And the particles he discovered are held behind the most absolute gate in existence, a confinement so total that the universe will spend your own energy manufacturing new matter rather than let you see a single one of them alone. Refusal made him. Refusal broke him. And refusal is the deepest law governing the thing he found. I do not know what to do with a symmetry that exact except to look at it and feel the floor tilt. Here is what it means for you, sitting there, in your body, right now. You are made of things that were denied. The quarks in you were denied their freedom in the first flicker of time and have been captive ever since. They are denied to your sight by a law that no bigger machine will ever overcome. Their permanent hiddenness is denied a full explanation by mathematics that no one on Earth has been able to complete. $1 million problem sitting unsolved because the flaw under everything resists being proven even as it holds you up. And the man who first insisted these denied and hidden and unexplained things were real was himself denied, hidden from the story, and left, in the end, with an unpleasant aftertaste and a career spent looking for hidden structure in ears and earthquakes and markets, anywhere but the field that could not forgive him for being right in a way it had not approved. When you knock on the table tonight, when you feel it stop your hand, remember what that solidity actually is. It is not the hardness of little pieces of stuff. It is the felt pressure of a refusal, the strong force declining to be compressed, the energy of a prison pushing back against you. 99% of the weight of the world made of the binding energy of captives you will never meet. Everything you have ever touched was the universe saying no. And somewhere in that no, in the deepest structure of the ordinary solid world, is the vindication of a man your textbooks left out, a man who looked at the impossible fractional charge particles that everyone said could not be real, and said, quietly, at the cost of everything, they are real, they are in there, one day we will understand. He was right, they are in there, they are in you. And we still do not understand, and we may be built in such a way that we are not permitted to. Richard Feynman, who broke the habit of a lifetime to try to get George Zweig a Nobel Prize he never received, is gone now, and Gell-Mann is gone, and Van Hove is gone, and the anonymous theorist who called Zweig a charlatan in a closed room is gone, his name having died with him, unrecorded, so that even the villain of the story got the anonymity that the hero was denied. The prizes have all been handed out, the Eightfold Way, the Deep Inelastic Scattering, the November Revolution, Asymptotic Freedom, medal after medal orbiting the idea, and not one of them with Zweig's name on the front. The word quark has conquered the language so completely that you had probably never heard the word aces until tonight. And the document sits in the archive, correct, complete, forbidden, describing you. The particles are real. George Zweig was right about the one thing that got him destroyed, and the reward for being right, the reward reality itself handed him, is that the thing he was right about is the one thing in the entire universe you are forbidden to see. He spent his life reaching for a truth behind a wall, and he found it, and the truth turned out to be a prisoner behind a wall that gets stronger the harder anyone pushes. You are made of that prisoner. You always were, and the last thing this universe will ever permit you to do, no matter how hard you look, no matter what you build, no matter how much of yourself you pour into the reaching, is to meet the thing you are made of, face to face, alone, in the light.